In this video, I want to remind you of the definitions of the trigonometric functions, and I want to show you a technique for creating a table that contains all the values of the trig function, sine and cosine, for the special angles that you're familiar with. So 0, 30, 45, 60, 90 degrees, and then their corresponding radian equivalents. So 0, pi by 6, pi by 4, pi by 3, and pi by 2. And then from that you can, if you don't remember all the values of the trig functions in special circumstances, this table allows you to kind of generate those values on the fly. So to begin, I wanted to remind you that the sine and the cosine, their origin, their definition, really comes from the unit circle. You take the unit circle and you trace around the unit circle in a counterclockwise fashion, and from this motion, or from these points, you extract the x component and the y component of those points. So if I draw in a specific point, so let's draw in a point and call this x comma y. Okay. Now the value of cosine is the link between this horizontal component, this x value, and the angle that we need to rotate through, the amount of the circle we need to cover to get to this point. So to understand the connection between these components, the x and the y, and the sine and the cosine, all I need to do here is draw in a triangle that links the point xy to this circle right here. Okay? So we have the unit circle, so I'm going to draw a line that goes from the origin right to the point xy. I'm going to drop a vertical line, which is going to create a little triangle. Okay? So you have a triangle right here. Now the sides of that triangle are actually the x and the y components of this point. So this horizontal side right here is x. The vertical side, that length, is given by y. Okay? And we can link this to the trigonometric functions if we draw in the angle here. Let's call this theta. That's a pretty standard notation to use for an angle. So I'll call that theta, and that's going to be the angle from the positive x-axis up to the hypotenuse, this diagonal line here. If we're drawing the unit circle, that guarantees that the radius there, that line that connects the origin to the circle at the point xy, has length 1. Okay? Now, many of the identities satisfied by the trigonometric functions come from this diagram. This is kind of the core of a lot of the relationships between sine and cosine. What I want to do right now is I want to show you how this picture gets connected to the graphs of sine and cosine. So it explains why those graphs look the way they are. I'm just going to draw some rough graphs of sine and cosine to give you an idea of what's going on, and then I'll show you how to use a table to get the precise values of sine and cosine at the special angles. So let's draw in a set of coordinate axes, and I'm going to put in some important values of theta where the trig functions do hit some important points. So let's say pi by 2, pi, 3 pi by 2, and 2 pi. Those will be the marks that I put on the horizontal axis. This is going to be the theta axis, and I'm going to draw on the vertical axis. I'm going to take the values of sine and cosine respectively and plot those. Okay? So let's draw in another coordinate axis so we can draw sine and cosine separately on two separate axes. Okay, so we're going to go from 0 to 2 pi. So we're going to go around this unit circle exactly once. All right, we'll see what the graphs look like on that for that domain. And then we'll look at how we would extend that to other values of theta, either negative values of theta or values of theta greater than 2 pi. See what happens there. So on the top, let's do a graph of cosine. And on the bottom, let's do a graph of sine of theta. Okay? So what you should do as you're watching the video is you should trace what's going on in the circle and make sure that it corresponds to the picture that I draw when I graph out these functions. So let's look at the first quarter of the circle. So starting out with theta equals 0, that's going to be at this point on the far right of the circle. And we're going to trace the circle in a counterclockwise fashion. So we're always going to rotate around in that direction. So I want to get from this point on the circle up through the first quarter of the circle to here. Okay? If I look at what's happening to the x-coordinate, and the x-coordinate is going to tell me what cosine is doing. So the x-coordinate is the adjacent side for this angle, and that's going to tell me what happens to cosine. So on the first quarter of the circle, the x component starts at 1. We start at the point 1, 0, and we rotate through this quarter of the circle, and we end up at the point 0, 1. So the x component starts at 1 and goes to 0 over the first quarter of the circle. So if I try to draw that in here, here's the value of 1 for theta equals 0. As theta goes to to pi by 2, that's the quarter of the circle, that x component goes down to 0. Right? On the next quarter of the circle, from pi over 2 to pi, and if we're measuring theta in radians, or from 90 degrees to 180 degrees if we're measuring in degrees, this x component starts at 0 and goes to 1. We're looking at what's happening horizontally now. Starting at 0, going to -1. So the next quarter of the circle, the plot of cosine looks like that. This is a height of -1 here. Okay? And then finally, we're going to look at the bottom half of the circle all at once. The x component starts at -1 and goes all the way through 0 up to the value 1. So as I graph the next piece from pi to 2 pi, this bottom half of the circle, the x component starts down here, makes it through 0, and goes all the way to 1. And if I've drawn this well, the height here should match up with the height here. So this is just a sketch, not perfect, but it gives you the right idea. Okay? So that's the graph of cosine from 0 to 2 pi. If we kept going around the circle, we tried to go around the circle again, we'd see the same pattern would repeat itself. So the cosine function is going to be periodic. It repeats the same information again and again and again each time you go around the circle. So I'll draw a little bit of the graph. And what I'm doing is just drawing the same kind of values or the same sequence of values we see here. Right? It's just a repeat of that. Now let's draw a sketch of the sine function using the same idea. This time we're going to track the y component. So if we start at this position on the circle, this is with theta equals 0, we see that at that point y is equal to 0. We're on the x-axis. So we're going to start the graph of our sine function at 0. Okay? Now as we go through the first quarter of the circle, that y is going to start at 0 and make it all the way to 1. So on our graph, we want to start at 0 and go all the way up to +1. Okay? If we do the next quarter circle, the one that's slightly in red if you look really carefully at the video, the y value is going to start at 1 and make it back down to 0. Okay? So the next, from pi over 2 to pi, or from 90 degrees to 180 degrees, we expect the graph to get back down to 0, the y component to be 0. Then, let's think about the bottom half of the circle all at once. We want the y value to go down to -1 and back up to 0 for the second half of the circle. So, from pi to 2 pi, we want to go down to -1 and back up to 0 when we graph sine. Go ahead and do that. And the graph looks something like that. And just like the cosine, if we went around again, if we tried to see what the graph of this function would look like for theta outside the interval from 0 to 2 pi, we'd see that this pattern repeats itself. So the next part of the function is going to look like this, which is just a repeat of these values right here. If we drew in some of this plot for, say, negative values of theta, we would see that looks like that. So this piece of the function matches the values of this piece of the function. Okay. So we get sine and cosine. This is what their graphs look like. We know that they're periodic because we keep repeating the same x's and y's as we go around the circle multiple times. But what we'd like to also be able to do is to nail down or specify some of the values of these functions for angles or triangles that appear quite often. Okay, so we have a few special triangles, a 45-45-90 triangle or a 30-60-90 triangle, where the sides of the triangle are expressible in a precise mathematical way. So we can express their relative lengths in terms of exact radicals and square roots and things like that. So what I want to do now is I want to show you a way to write down a table which will give you the values of sine and cosine in a very simple way. You learn how to draw the table or write down the table, and you don't need to memorize all the values separately. So this pattern that I'm about to show you does not generalize. It doesn't help you to find the values of sine and cosine in between the special angles, but it is pretty useful for finding the values for all the standard special values. So 0, 30, 45, 60, 90 degrees, or 0, pi by 6, pi by 4, pi by 3, pi by 2. So when I draw out this table, I'm going to leave the graphs that you see here, and we can use those to double check and make sure that the table seems to be doing the right thing. So let's go ahead and draw in. It won't be perfectly to scale, but we'll try to fit in as much as we can. So I'm going to draw a set of angles, and I'm going to use radians to represent my angles. If you want to use degrees, you can do the conversion yourself. So we're going to start out with 0 radians. Then the first special angle is 30 degrees, or pi over 6 radians. So this is going to be a measurement of theta up here. And then below that, I'm going to put measurements of sine theta and cosine theta. We have pi by 6, pi by 4, pi by 3, pi by 2. Okay, that gets us up to 90 degrees. I'll show you how to extend the table further than this in a minute, but I want to show you how to produce the table first. Okay, so first I'm just going to make one row for the cosines and one row for the sines. And I'll put the cosines on top, just like I put arrange the graphs here. So we're going to put cosine of theta, the value of the function, in these rows, or these cells. And then we'll put the values of sine of theta below that. Now the trick about this table, the thing that makes it easy to produce, is you only have to remember a few things, and then the table extends out using the pattern that you establish. When you might learn these values of the trig functions in a standard Algebra 2 class or trigonometry class, you might remember reduced forms of the values, but here we remember the values in a way that they look pretty. They have kind of a very nice symmetry, a nice organized pattern that they follow. But that means that some values that might seem simple are written in a more complicated way in the table. So what exactly am I talking about? All right, so when we create this table, what we're going to do first is every number that appears in the table is going to be divided by 2. Okay, so I'll just put divided by 2, divided by 2, divided by 2, divided by 2, divided by 2. Okay, same thing with the sine values. I'm going to write them all divided by 2. So that's something, once I know that I'm going to construct this table, I know that everything gets divided by 2, and I don't worry about it. I just put 2 in the divisors of everything that's going to go into the table. So I don't need to think about it, I don't need to memorize it. That's one thing that's going to attach to all of the numbers, all the values in the table. Next, what I need to do is I need to remember, this is important, I need to remember the values of sine and cosine at 0. Okay, so I want to make start the table off correctly. So if I look at the graph, we see that cosine of 0, the value of cosine at 0 is 1. So now, the next thing that goes in everywhere in the table is a square root. So we put a square root everywhere. and you'll see why in just a second. Square root everywhere. And now I use the value of cosine to pick what goes into that square root. So the cosine of 0, the value of the cosine of theta when theta is equal to 0, is 1. I want to choose the value that I put into this square root to make the whole value, to make the value on the table equal the right thing. So the square root, I need the square root to be 2. So if I put a 4 in, the square root of 4 is positive 2. 2 divided by 2 is equal to 1. So that gives me the right value for cosine. Now the sine of 0 is 0. So I ask myself, what should I put into that square root to give me the right value? And the answer is just 0. Okay? So now we've set the stage. Now let me show you what the pattern is. So what I'm going to do is now over all the special angles, we're just going to count up and down. So the cosine, we know that it's decreasing, so we start at this whole expression being equal to 1, and we just count down inside the square root. So at the next special angle, the value of cosine is the square root of 3 over 2. At the next special value, pi over 4, turns out the value of cosine is square root of 2 over 2. The next value, we see square root of 1 over 2. And at the next value, we see square root of 0 over 2. Okay? Now these are a little bit more complicated than they need to be. Of course, square root of 4 divided by 2 is equal to 1. But by putting the values of cosine in this way, I don't have to remember them all individually. All I need to remember is the pattern. I know that everything in the table has a square root. Everything in the table is divided by 2, and each number in the table is achieved or reached by counting either up or down from a previous value. So cosine goes from square root 4 over 2, which is 1, down to 0, or square root 0 over 2, at the special angle 90 degrees or pi over 2. For the values of sine, we simply count up. We start at square root 0 over 2. The next special value is square root 1 over 2. The next special value is square root 2 over 2, square root 3 over 2, and square root 4 over 2. Okay? So from that table and that pattern, we now can extract the values of sine and cosine at any of the special angles that we might be interested in. You can continue this pattern at the special angles in the second, third, and fourth quadrants if you want. What you do is you continue this counting process. You count up and down from between -4 and +4. So the next thing we see, which is pi over 2 plus pi over 6, would be negative square root 1 over 2. Okay, so that's pi over 2 plus pi over 6. You can go ahead and find a common denominator if you want, but this is the idea. So you continue to count. You change the input to the square root by one integer, and we continue going down. As we continue this process at pi, that next special angle, the pattern extends so that cosine is negative square root 4 over 2. And then with the sine function, once you get up to 1, you start counting down again. So we see square root of 3 over 2. We count up to 4, then back down from 4, and then at pi, we'd be down to square root 0 over 2. If you wanted to figure out the special values in the third and fourth quadrants, you'd keep going with these patterns. You go all the way up to square root 4, all the way back down to negative square root of 4, and then you would continue back up. So the next pi plus pi over 6 would be negative square root of 3 over 2 in the cosine, and then in the sine function, we're in the midst of counting down, so we'd see a negative square root 1 divided by 2. So this gives you kind of an efficient way to get all those values of sine and cosine that you might have spent the time memorizing individually in a high school class. What you find is most of the time in practice, You could use a calculator to extract the value of sine or cosine if you need to. Or you just leave the answer in terms of the values of sine or cosine that you see. But if you absolutely need a number and you don't have any technology at your disposal to get that, a table like this can make it a very efficient way to get the values that you need. Okay? So that basically covers what I wanted to talk about in this introductory video, just reminding you of the definitions of the cosine and the sine, right? How they're connected to the unit circle, and what their graphs look like, and a special way to extract the values of these functions at the special angles. Okay? Before we finish, I want to show you a few trigonometric identities that are extractable or can be deduced just from the definitions of sine and cosine. And then I want to remind you, in addition, of the definitions of the other trig functions, the derived trig functions, and how they connect to sine and cosine. All right, so let me clear the board, and we'll look at those things. So let's write out the derived trig functions and their definitions. We have the tangent function, which is defined as the sine function divided by the cosine function. We have the cotangent function, which is the reciprocal of that. That's the cosine divided by the sine. We have the secant function, which is 1 over the cosine, the reciprocal of cosine, or the multiplicative inverse of cosine. And we have cosecant, which is 1 over sine. One way that's helpful for remembering which trig function corresponds to which, or which is the reciprocal of another, every pair of trig functions has one co in it. Okay, so we have tangent and cotangent, and those are reciprocals. We have cosine and secant, and those are reciprocals. And we have cosecant and sine, and those are reciprocals. Okay? Whereas the sine and the cosine are the kind of original trig functions coming directly from the unit circle. Okay? There are a wide variety of different identities or connections between the trig functions that are useful in a lot of different circumstances. Right now, I want to show you what are called the Pythagorean identities, which come from this connection between the components of the circle and the Pythagorean theorem. If you remember from maybe a geometry class or a regular middle school math class, you might have learned that when you have a right triangle, a triangle that contains a 90-degree angle, there's a connection between the lengths of the legs of the triangle and the hypotenuse of the triangle. Standard notation, the normal way that you see this is something like if one side is length A, another side is length B, the hypotenuse is C, then there's an algebraic relationship between those three numbers whenever this is a 90-degree angle. The Pythagorean theorem says that that relationship is that the square of A plus the square of B is equal to the square of C. All right? Now, if we apply this to our triangle that appears in the definition of sine and cosine, we immediately get what's called the Pythagorean identity for sine and cosine. We see that we chose x equal to cosine of theta, so the bottom length of this triangle here is cosine of theta. The vertical leg of this triangle is the y component, and that's the definition of sine theta. And when we're using the unit circle, this diagonal line, no matter where we put it, is always the hypotenuse of the triangle, so that corresponds to the C. Right? So if we substitute in the cosine, the sine, and this unit hypotenuse into the Pythagorean theorem, we get one of the Pythagorean identities. Okay? So the bottom leg here is the cosine function. We have cosine, say, of theta squared plus this b, that's our vertical leg, and that is sine. So we get sine of theta squared. And the c, when we are thinking about the unit circle, that c is length 1, so 1 squared is 1. This is the first Pythagorean identity for the trig functions. It says cosine squared plus sine squared is equal to 1. That balance is true for any theta that we choose, anything between 0 and 2 pi. Any triangle we draw around the circle, we always get this connection that cosine squared plus sine squared is equal to 1. So that's kind of a constant relationship that you can always go back to if you want to manipulate or convert from sines to cosines. In addition, it can just be a simplifying identity. If you have a cosine squared and you have a sine squared and you're adding them together, their sum can always be simplified down to its a constant value of 1. Okay? All right, so this is the main Pythagorean identity, and by manipulating this in different ways, we can get some other Pythagorean identities that are connected to the derived trig functions. So I'm just going to show you 2 of those really quickly. If we take this Pythagorean identity, cosine squared plus sine squared is equal to 1, and we divide by, say, cosine squared, that allows us or gives us a different connection between sine and cosine. And then if we connect that to the derived trig functions, we arrive at another Pythagorean identity that you might use. So I'm going to divide everything in this equation by cosine squared. Right? If I divide the first term by cosine squared, those terms cancel out perfectly. I'm left with 1. In the second term, if I divide that by cosine squared, these don't cancel out perfectly, but I get something that I can write in terms of the derived trig function tangent. I can write that ratio, I can write that fraction as tangent squared. On the right-hand side, if I divide by cosine squared, I get something that's complicated, but I can write it in a simpler way by using the definition of the secant function. Okay, so if I take the original Pythagorean identity, cosine squared plus sine squared is equal to 1, divide everything by cosine squared, the result is 1 plus tangent squared is equal to secant squared. Okay. And this is another Pythagorean identity. This is something that you can use in any situation where it might be helpful. All right. The last Pythagorean identity that you might want to be familiar with is obtained in the same way that we just obtained this 1 plus tangent squared is secant squared. We're just going to divide by sine squared everywhere. If I divide this first term by sine squared, nothing cancels out, but we can write that ratio in terms of cotangent. Dividing the second term by sine squared, these cancel out perfectly. I'm left with 1 sine squared divided by cosine squared. Those cancel out. And on the right-hand side, if we divide by sine squared, we get something that we can write in terms of cosecant. Right? So we get a different trigonometric identity. These 3 together are called the Pythagorean identities. So let me just write these nice and clearly, one at a time on the board, and then that'll conclude this kind of introduction to the trigonometric functions. So we have the core Pythagorean identity, which is cosine squared plus sine squared is equal to 1. we have the version of the Pythagorean identity we get when we divide everything by cosine squared, which is written as 1 plus tangent squared is equal to secant squared. And then we have the version of this Pythagorean identity we get if we divide everything by sine squared. And that looks like cotangent squared plus 1 is equal to cosecant squared. So these are three different versions of the Pythagorean identity that you can use to convert one trig function into another, or to just simplify. So this sum of squared trig functions is equal to 1. If I manipulate this second identity by subtracting tangent squared from both sides, I can see a difference of secants and tangents must also be equal to 1. Okay? And the last one gives us a connection between the cotangent and the cosecant. So what you'll find is you'll have lots of different problems where you see some combinations of trigonometric functions, sines, cosines, tangents, whatever it happens to be, and oftentimes you need to manipulate or adjust those to simplify or to evaluate them for different purposes. And these trigonometric identities, they give you flexibility in converting one trigonometric function into another trigonometric function. So they can be used to really make your life easier in a lot of different circumstances. And they come from just this simple triangle that we draw in when we define the sine and the cosine function. Okay?